Okay, so we know that we can always plug in a value of the explanatory variable, calculate it with the formula and predict the response. But how accurate is that? So there's actually two different ways to think about this. So a confidence interval is for the mean response. So basically, this is giving you a range of plausible values for the population mean at a specific x value, right? So if you think about, let's just pick a point, maybe like 180, and we can think about all the people who have a total cholesterol of 180. We want to know what's the mean BMI for that person. So that's what a confidence interval tells you, and that's the narrow one here. So when you're trying to estimate the mean, you're going to use this narrow interval. So it's a 95% confidence interval, and this is the narrower of the two that are shown. Okay, so another way to think about this is trying to capture the true regression line. Right, the true regression line is showing you the mean response at any particular value of x. So this is intended to capture the true regression line. But maybe you're not interested in the mean value. Maybe you're interested in predicting for an individual, right? This is giving the range of plausible values for an individual at a specific x value. Okay, so here, if you're talking about individuals, individuals are going to vary a lot. So this is going to have to be a lot wider. So this is our 95% prediction interval. And if you're looking at the two on the graph, this is going to be the wider of the two. Okay, so this is intended to capture most individuals. So if you're talking about like a 95% prediction interval, you're going to capture 95% of the individuals, or at least that's the idea. Okay, and we're actually going to leave a little bit of space here because we're going to come back and talk about this later. I did want to make a connection to the validity conditions because in both of the examples that we've seen in this chapter, there were at least some concerns about the validity conditions, and they come up when we talk about confidence intervals and prediction intervals. So let's talk about the BMI example first. So when we saw the BMI example, we had non-normality of the residuals. And if we make a histogram or something like that, we can actually see that the residuals are skewed to the right. So how does that affect the intervals? So if you look at this graph up here, notice that there are a lot of individuals that are above the upper bound, right? So we have many individuals that are above the upper bound of the prediction interval. And we don't want that. We want to be able to capture most of the individuals. But because it's skewed right, you just sort of have more high BMI people than you would have expected under normality, right? So the prediction interval isn't accounting for that skew, and you end up with a lot of people that are outside the bounds of your prediction interval. So even though there's a really big sample size in this example, sample size can't fix this. So sample size doesn't fix the prediction interval. On the other hand, if we think about the validity of the confidence interval, that's actually probably going to be okay. And it's for the same reasons that sample size fixed the issue when we were doing a t-test for means earlier. So you end up with a pretty nice normal, or at least bell-shaped sampling distribution if your sample size is large. So we're not fixing the prediction interval problem, but the confidence interval is probably okay. Okay, what about the house prices example? So with the house prices example, we saw non-constant variance, right? We were worried that we might have a little bit of a funnel shape here. So the problem is, if you look at the prediction interval on each side of the mean, it's assuming that your spread is the same. So that prediction interval assumes the same level of spread for high and low values. So the prediction interval is also going to be a problem when you're talking about non-constant variance.